Hello, and welcome to Exponential Functions and their Graphs. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This lecture is for Math 1508 at UTEP. Chapter 3, Exponential and Logarithmic Functions, comes to us from Larson's Pre-Calculus 10th edition. Section 3.1, Exponential Functions and their Graphs. So let's start with a definition. The exponential function f with base a is denoted by f of x equals a to the x, where a is positive and not equal to 1. X is any real number. So we have our domain here. X is any real number will give us our domain. So the domain is all real numbers. Secondly, a note, there are other functions that look similar where we don't have these restrictions on a. You could have an a that's a negative number, but we don't call it an exponential function. So they exist, they're just not in the class of functions we're discussing right now. So the graph of f of x equals a to the x has one of two basic forms. If the a value is between 0 and 1, the graph will be decreasing. If the a value is larger than 1, the graph will be increasing. Either way, the graph of f of x equal a to the x has a y-intercept of 0, 1, and it's a one-to-one monotonic function. Monotonic, mono meaning one direction, not the band. Talking some math here. Monotonic means it's either always increasing or always decreasing, and in this case it depends on the a value. The domain consists of all real numbers, and the range are y values greater than 0. No matter what the base is, given our certain conditions, putting in any value of x, whether positive, negative, or what have you, we can never make a negative value come out of this. So the domain, all real numbers, the range, positive values. When the a value is between 0 and 1, we might think of it as a horizontal reflection instead, so we'll call that f of x equals a to the negative x as long as a is greater than 1. I'll show you a little bit about what I mean by that in a minute. So here we have our basic shapes. For an a value that's a proper fraction between 0 and 1, it's going to be decreasing. For an a value that's larger than 1, our graph is going to be increasing. What I was talking about with, say this is the graph of f of x equals 2 to the x. Alright, that's not an x. Let's make that to an x. Suppose that's a graph. What I can do is, if I take the graph of f of x equals 1/2 to the x, and I flip it, so I'm going to introduce a negative in front of the x, so we're looking at a horizontal reflection. All I'm going to do, a horizontal reflection, it's now going to look like this, which is exactly the graph where a is larger than 0. So that's what it meant in that last slide, where if the a values are between 0 and 1 are proper fractions, we sometimes think of this graph, the graph of f of x equals 1/2 x, as the reflection of the graph f of x equals 2x. Alright, so let's graph some and see what's going on. We're going to label at least 3 points with exact values, so no decimals here, exact values. We'll just suck it up and deal with fractions. If f of x equals 6 to the x, I get to choose my x values. They're independent, so I'm going to choose an x value of -1. 6 to the -1 is 1/6, so I'll have the point -1, 1/6. An x value of 0, 6 to the 0 is 1. Anything other than 0 raised to the 0 power is 1. And 6 to the first power is 6. So I'll have 0, 1, 1, 6. And using Desmos.com, I have a very pretty looking graph of f of x equals 6 to the x. Remember, you get to choose any values you want for the x. But once you choose them, you have to find the y values. I try to use the easiest ones possible. X equals -1, 0, and 1. For a g of x equals 1/2 all to the -x power, we could think of that as the same as the graph of f of x, or excuse me, g of x equals 2 to the x. But let's do it as the original states. When x is -1, I'll have 1/2 to the negative 1 power, but a negative 1 is positive 1. 1/2 to the first power is 1/2. When x is 0, 1/2 to the negative 0 power, well, 0 is not positive nor negative, so 1/2 to the 0 is 1. When x is 1, 1/2 to the negative, given to us from the problem, 1, is reciprocal, so that's 2. At negative 1, we have a half, 0, 1, 1, 2. It's the same as the graph of g of x equals 2 to the x. If h of x equals 4 times x minus 2 plus 3, let's just see what happens. Using Desmos, we have a nice looking graph, so I'm not going to try to graph it by hand. I could use small values. If I start with my same basic values, negative 1, 0, 1, and then I'm going to add a few more, 2 and 3. We'll substitute negative 1 in for x, 4 to the negative 1 minus 2, and then plus 3. That's 4 to the negative 3, it's 1 over 64 plus 3. Absolutely, I'm going to leave that in fraction notation. My point is negative 1, 193 over 64. Yep, that's right there. When x is 0, I'll get a y value of 49 over 16. Notice it's no longer the y-intercept of 0, 1, and that's because we've shifted to the right 2. We've shifted the graph up 3. So there's a lot going on here. Simplifying x values of 1, 2, and 3, we'll end up with negative 1, positive 1, 13 fourths, 2, 4, and 3, 7, and there's our graph. Notice that it does seem to approach this asymptote, really poorly drawn asymptote, but the asymptote is the horizontal line, y equals 3. So let's use the graph to describe the transformations that yields the graph of g. If we start with f of x equals 3 to the x, and I add 1 on the outside after I've done the exponential, well, then it's going to shift up 1 unit. If I start with f of x equals 10 to the x, and I'm looking at 10 to the negative x plus 3, well, I'm going to factor out the negative. Factor this negative out. Anytime there's a negative associated with the x value, it's going to be a horizontal reflection across the y-axis. And so we really need to simplify this negative parentheses x minus 3 so that I can see I have shifted right 3 units and reflected across the y-axis. So a horizontal reflection because it's dealing with the x value. We have this number. It's called the natural base. It's named after the German mathematician Leonhard Euler. Just a side note, one of my favorite movies of all time, Bill and Ted's Excellent Adventure. All the pictures I've seen of Euler, he looks just like the Royal Ugly Dudes. Check it out. You'll probably hate me for making you watch that movie, but I love it. Many times, the most natural base to use is the irrational number e, which is approximately 2.71828 ... It never repeats. It's an irrational number. This is called the natural base, and it comes to us actually from a finance formula. If you want to know how e is actually defined, take calculus. We'll get there. The function given by f of x equals e to the x is called the natural exponential function. Keep in mind, I know that e is 2.7 and so on. So it's larger than 1, so I know that this is a graph that is increasing. It has a y-intercept of 0, 1. Never use the decimal approximation or a simplified version of the decimal approximation. Always use the exact value of e on your calculator, which you can find generally as a second function of the ln button, the natural log. Alright, so f of x equals e to the x. We're going to use this for some finance formulas. Let's start with compound interest. After T years, the balance A in an account with principal P and annual interest rate R in decimal form always is given by the following formulas. A equals P parentheses 1 plus R over N to the power of NT. And for continuous compounding, so as N gets larger and larger, so more and more compoundings per year, this goes to, it becomes the equation A equals P e to the RT, and I put in the parentheses to remind yourself if something's going on in the exponent, put parentheses around it so your calculator knows there's something going on in the exponent. The only thing I haven't really defined here, t is our time in years, and the n value will always be given in words such as annually, monthly, quarterly, daily, hourly, semi-annually, and so forth. So if we want to complete the table to determine the balance A for $2,500 invested at 4% and compounded n times per year for 20 years, starting with an n value of 1, 2, 4, 12, 365, and then continuously, what I will use on my calculator is 2,500 parentheses 1 plus 0.04 decimal form over n to the power of 20 times n, and then I will substitute, put 1 in for n, and I get an answer of $5,477.81. Now put 2 in for n, and I'll get $5,520.10. Similarly, putting 4, 12, and 365 in for n, we can find our values. However, when it comes to continuous compounding, there is no n value. Continuous compounding compounds literally continuously. You're constantly making money. Sounds like my dream. So we use the continuous compounding formula. A equals PE to the RT. So in my parentheses, in my exponent, I have 0.04, my interest rate, times the time in years, 20 years. And I will enter that, 2,500 e to the power of 0.04 times 20. And I end up with a $5,563.85. You can see we've gained quite a bit of money. Well, okay, almost $100 from annual to daily. But in daily to continuously, we gained 24 cents. So getting daily interest rate, that's pretty good. It's almost as good as continuous in the short term. 20 years, that's considered short term. Another example of where we use exponential forms. The number V of computers infected by a computer virus increases according to the model. V of t equals 100 e to the 4.6052t, where t is the time in hours. We're going to find the number of computers infected after 1 hour, 1.5 hours, and after 2 hours. So after 1 hour, we'll put 1 in for t. So that's 100 e to the 4.6052. And that gives us 10,000 computers infected after the first hour. A half an hour later, so when time is 1.5, now this growth is at 100,004 computers that are infected just a half an hour later. And then finally after 2 hours, substituting 2 for my time, letting the calculator do the work, we have over 1 million computers that are infected in just 2 hours. And this actually all starts with just 100 computers. So be careful when you're using somebody else's computer. Make sure you don't send this out into the world, at least not on accident. Thanks for listening.